Okay, today we're looking at similarity in specifically right triangles. And this first look is we're going to prove that the Pythagorean theorem indeed is a true statement, that we can square the legs, add them together, and that will be equal to the hypotenuse squared. So the given is that ABC is a right triangle with legs A and B and hypotenuse C. We're going to prove that when we square A and add it to B, it's equal to C squared. So we're going to draw a perpendicular from C to the hypotenuse. This basically is an altitude, and label the point X, X being the point where that altitude hits the hypotenuse. Angle BXC, let me move my picture over. BXC is congruent to BCA because they are both right angles, and we'll see they're both right angles, so yes. And the reason we can say that is all right angles are congruent. Well, angle B, so let's go ahead and mark that as congruent. So that's congruent to that. And angle B is congruent to angle B because of the reflexive property. So BXC is similar to BCA. Now we have two separate triangles, but notice that we have two angles that are congruent in each. I have the large triangle with this angle and this angle as congruent, and then I have the smaller triangle with this angle congruent and then this angle congruent. So we can prove that those two triangles are indeed similar because of the angle-angle similarity. Because of that, we can prove that AXC is this angle. It's congruent to ACB, not ACB, I'm sorry. Let's see. AXC is congruent to angle ACB, which is this angle, because that is the corresponding angle. And actually, no, I'm sorry, because it's AXC is a right angle, and we already see that ACB is as well. So again, that's all right angles are congruent. Angle A is congruent to angle A because reflexive property, so the same thing. So basically, both of those smaller triangles within the larger triangle are similar to each other. We proved that one by the same reason. Angle-angle similarity. Okay, so we've proven that the small triangles are congruent, or similar. They're all three triangles that are formed are similar. So now let's look at the proportions here. Let the length of the segments A be DE as shown in the figure. That's the hypotenuse. So D and E is the hypotenuse, which is C. And we're going to prove that corresponding sides. So because BXC is similar to BCA. Okay, so since the two triangles are similar, A and C would correspond to E and A. Because you see those would be corresponding parts of the triangle. A is the leg of the large triangle. C is the hypotenuse of the large triangle. E is the leg of this middle-sized triangle, and A is the hypotenuse of that same triangle. So those are corresponding parts. Now proportion 2, we'll be looking at the smaller triangle. B over C. B is the hypotenuse of the small triangle. C is the hypotenuse of the large triangle. And that would correspond to the leg of the smaller triangle, which is B. I'm sorry, the leg of the larger triangle, which is on bottom, which is B, and then the leg of the smaller triangle, which is D. Okay, so those would be the proportions that we would have. Now perform some algebra to complete the proof as follows. Multiply both sides of proportion 1 by AC. So if we have, and I'll write that over here on the side. Actually, let me zoom in and do it here. Looking at number 1, multiply both sides by AC. So we would have A over C equals E over A. And we're going to multiply both sides by AC. Okay, that would cancel that out. That would cancel that out. So we would be left with A times A, which is A squared, equals E times C, which would be EC. Now multiply both sides of proportion 2 by BC. So proportion 2, remember, was B over C equals D over B. And we're multiplying it times BC. So that would cancel the C's out, cancel the B's out. So we'd be left with A times B, which is B squared, D times C, which is DC. Okay? Adding the above equations gives us this. I'm adding the same thing to both sides, so I can say A squared, if I add this, I add this plus this, it's the same as this plus this because both sides are equal to each other. So A squared plus B squared equals EC plus DC. Factor the right side, so we still have A squared plus B squared. That's going to be equal to, factor a C out, C times E plus D. Finally, use the fact that E plus D equals C. We saw that in the diagram. So we can change that to A squared plus B squared equals C times C, which gives us the Pythagorean theorem. Okay, don't get hung up on all that. Just know that because of this proof that we just did, we don't have to wonder if the Pythagorean theory works every time. It does. All right, so now we're going to talk a little bit about the mean and what it is, specifically the geometric mean. Okay, so I have two numbers, and I have the mean, and then I have the extreme. What this means is these are the numbers I'm dealing with. Okay, they are the extremes. The mean are the numbers in the middle that I'll be multiplying. And what we're working with, if we have the mean where it's x, the same number, we end up with x equals the square root of a times b. Okay, we'll see more specifically what that means. It means that if I have a over x equals x over b, well then x squared is equal to the square root of ab, which makes sense because when I cross multiply that I get x squared. I cross multiply that I get ab. If I want to find out what x is, I square root both sides, and x is going to equal the square root of ab. That's when I have the same number multiplying it. So if I'm finding the geometric mean between 8 and 10, what I do is, okay, so if we're finding the geometric mean between 8 and 10, we could write 8 over x equals x over 10. Cross multiply, get x squared equals 80, and take the square root of both of those. Or we can just say that x equals the square root of 8 times 10. Either way, we get the same thing. And if we simplify that, or if we put it in our calculator, it would give us something similar to 8.9. Okay, and you'll start to see how this is going to work with our problems here in a minute. If the altitude is drawn to the hypotenuse of a right triangle, the altitude which separates it into three small triangles, then the two triangles formed are similar to the original triangle and to each other. We saw that in the proof. Write a similarity statement identifying the three triangles. So let's talk about the big one. We'll go FGH. So we'll say triangle FGH, that should be an H, is similar to triangle. Well, F is the short side of the big triangle. So let's look at the middle triangle, this one right here. Now, if FG, the first two letters that I used in the large triangle, is the short side, then what would the short side be of this triangle? Well, F would correspond to G because they are not right angles and they are part of the short side. So we're going to go with G here. Notice that J is a right angle, G is a right angle, so J is going to be next, and then H would be next. And that's going to be similar to triangle. Now we're looking at the small one. The short side is FJ on that triangle. When I say the small one, I'm talking about this. F and J are make up the short side, FJ. J is a right angle, so F is going to be next. J is the right angle, and then G is opposite the short side, so we're going to go G there. Okay? Okay, in the last section, we're going to look at how we can use this to solve the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of this altitude is the geometric mean. Between the lengths of these two segments. What that means is I have corresponding parts x over h. Now I'm looking at the smaller triangle on the left. X is the short side, h is the long leg, and that's going to be congruent or equal to the ratio h, which is the short side of this triangle, over the other leg, y. So when I multiply the two, cross multiply, we get h squared equals xy. To find h, we take the square root of both sides, and we find that h equals radical xy. So these the two segments formed by the altitude, are the geometric mean of the triangle. Okay, so let's look at this. Solving these problems, we're going to solve for the missing variable. Remember, the geometric mean is these two numbers, the square root of these two numbers. Now, if I'm not looking for the geometric mean, then I can just use that formula, or what I used a minute ago, of x over h equals h over y. And remember, this would be h, this would be x, or this would be x, this would be y. So we could say x over h, which is 4, equals 4 over 8. If I cross multiply, I get 16 equals 8x. Solve for x, x equals 2. Now look at this one. I don't have h. So I would say, if I solved it with a proportion, I would have 3 over x equals x over 9. X squared equals 27. If I take the square root of both of those, I get x equals 3 radical 3. Now, could I have skipped some of that in this case on number 2? Yes, I could have just said x equals the square root of 3 times 9, which is 27, which would have gotten me the same answer. Okay, number 3 is a little different. You just have to find out what this segment is right here, and you can do that by taking 27 minus 7, which equals 18. So now you know the numbers. 18 over x equals x over 7. Or you could just say x equals radical 18 times 7.